Hello folks, so I'd like to welcome you back to part 2 of our series on reverse engineering the Siemens Alpha inverter, Elfa2 I should say. So purposes of this, if you're just joining us, is so we can build our own custom version of this logic board to allow us to control the rather nice power stage. So, some people on the last video gave me links to a very useful manual for the inverter, and that allowed me to see what the pin connections for this main input connector are. And as such, I've now got a multimeter just set to continuity. I've got the negative multimeter probe connected to the ground pin, and I've got a probe here, and what I do then is I just run the probe down the length on both sides of the pins, and you'll hear it beeps a few times. So what that's telling us is we're picking up a direct ground connection, and that lets us get started on working out what the pin functions are. This is a 50-way, fairly fine pitch IDC header, and what I've done is I've gone ahead and I have just took a sheet of paper, just put down 50 dots on it, put some orientation marks and pin numbers here, and we're going to start off. The first thing is we're going to identify which of these pins are grounds, and we do that very simply. Let me grab my pen. Pretty much start with our multimeter here, and we just start going on each pin. So that tells me then that my top right pin is a ground, and then we just fill them in here on the little diagram. And our third one is a ground, and so forth. So I'll go ahead and identify all these grounds, and then we'll come along and we will start looking at the second phase, which would be identifying which of these pins provide power and what those power levels are. Alrighty, so right now for our logic board powered up, we've got 24 volt supply going to it. It's 24 volts because these are designed for use in trucks and buses and that kind of thing, which use 24 volts instead of 12 for their engine start and general lights and that kind of thing. So we've got it powered up. If anyone interested, we have, if I get the diagram for you, let's go up here on the computer. Works out, you put power on pin 1, ground on pin 2, and then you need a ignition on, just again at 24 volts on pin 27. So we have that. We're drawing about 200 milliamps just with the board idling here at the minute from our 24 volt supply. So we're not interested in feeding this thing CAN messages or what it's doing or anything like that. We're just interested in what the voltages on some of these pins, particularly voltages that would be indicative of a power supply. So what we do again is we've our grounds mapped out on our little diagram now. So we're going to take our multimeter, set to DC volts, ground connected to ground, and we're just taking our probe and we're just walking it around some of these pins, and so obviously this top right pin is a ground, so we see pretty much 0 volts on that. Now if we go to the second pin, things get interesting. We get minus 15.6 volts. Now that's much more likely to be minus 15 volts. I'm going to prove that to you now, because we're on the, let's say, the vehicle side ground at the minute. So that 15.6 is probably going through some kind of a diode or reverse polarity protection. So if I took my second multimeter probe and put it on the ground pin here, and then we probe onto our 15 volt supply pin, and oh, I'm proven wrong. It's indeed 15 minus 15.6 volts. So there we go. I thought I might have been seeing a diode voltage drop going on there, but okay, so that is minus 15.6 volts. Now we just keep going, so that's our minus 15.6. Got nothing there because that's a ground, as we found. Next one down there gives us a 5 volts. Now that could be a 5 volt supply, or it could be a 5 volt signal. One way of knowing that is sometimes to have a look at the board and see if it's if there's a heavy track or a via going down into another layer. Just mark that as 5 volts anyway. And we pretty much keep on going. I'm not going to film the whole thing. I'll come back to you guys when I've done a kind of a voltage map of all of these pins. And then the next phase of the operation will be we will start to look at our voltage map. Then we'll be connecting to the power stage and seeing if we can identify some of what goes on there. Now what we can do as well is we can start looking at some of the components on the gate driver board and working out what signal pins are what, but that's for later on. I'm just taking this very much step by step, just to give you guys a feel for what actually goes on when we get one of these pieces of equipment here and we don't know where to start. So okay, let's do it. Okay, so one thing I immediately noticed about the IGBT driver board was that obviously we've these transformers here to provide the isolated gate drive. So we've 4 transformers there and a 5th one up there, which is obviously for the isolated measurement of the high voltage bus. Now what we see here is that there's no switching elements or anything to drive the transformer primaries. So did a few voltage measurements around the primaries with the multimeter, and I was getting kind of strange voltages, but it related back to something that I'd seen on the logic board. So went over here and soldered on a pin here onto one of these heavy tracks, and we got our oscilloscope out, and on our oscilloscope, as you'll see here, we have a 65 kilohertz 32 volt peak to peak square wave, and this is what is driving the transformer primaries. And indeed, with just our system set up here on the bench, the IGBT drivers are enabled, and we're seeing minus 5 volts on the IGBT gate to emitter. So they are powered up and all transistors turned off, as we would expect. Now what we're going to do next is we're going to do a little bit of tracing work on the logic board to see how they're doing that drive for the transformers. And then we will have a look see at some of these traces here, where we can see, you know, potentially these are our driver traces, so we can just track those back to the logic board. We should be able to figure out how to turn on and off our IGBTs. Now you'll notice here that each driver has got 2 HCNW2211 opto couplers up here, each of them flipped. So this one is sending a signal from the driver back to the control card, and this one is sending a signal from the control card to the driver. So what you will have here is there will be a drive signal and there'll be a fault feedback here via this guy. So we'll be tracing that out as well. So this is just a little bit of a taster of what we get when we delve into these particular systems. Okay, so after some more investigating, we have discovered something rather interesting here. We have two devices, this guy here and here, which are 74HC541 octal drivers. This one here is taking signals from this Xilinx FPGA and feeding them to certain pins on here, which I suspect are my 8 IGBT driver signals. And this one here is taking signals back from the pins on here and feeding them back to the Spartan. So I'd imagine this one is for handling the error signals and this one is for handling the driver signals. So what we're going to do now is we're going to remove this chip, and this, because this chip is currently, its two output enable pins are currently pulled up, so this chip is disabled. There are some signals coming into it, but they're not getting through it because obviously this board is not in a running condition and there'll be various fault sets, so it's being switched off. So if we remove it, it should mean that the 8 pins here then are our IGBT driver signals. Alright, so in the last episode, or in the last clip, or whatever this is going to be, you saw that we had removed a 74HCT514 driver chip here. Now this gave us access to the 8 cathodes for the drive opto couplers on the IGBT driver board. But the problem is we had no anode power. Now a little bit of checking around showed us that the anode power for the L1, L2 and L3 are commoned together onto 3 pins on our header here. And the L4 is on a single pin. Each pin to the actual anode of the HCNR2211 opto gave us 600 ohms. Now, so we then have our 3 pins here that we're looking to find where they go. Now, the way that I employ to do this when it's a multi-layer PCB and it's not really possible to track, track tracks. So what I usually do is I take a little piece of wire that I can form into a brush like this. Now this isn't the best, it should be a finer kind of a wire, but this did the trick. You stick one end of this on one of your multimeter probes, get a continuity beeper, and then you kind of just start off on the pin that you want to find where it goes, and you just start brushing around the PCB. Now this lets you cover a lot of ground quickly, and when I got up here I started hearing little beeps, and that narrowed me down to this transistor here, which is a P-channel MOSFET. So that is the guy that controls our L1, 2 and 3 anode power, which is just plain old 5 volts DC. And this one here controls our L4. So what I'm going to do, just for simplicity's sake, is I'm going to go ahead and just short the drain to source on both of these transistors with a little, I'm just going to solder a piece of wire across the drain to source, and that'll keep the 5 volt power on, and hopefully then by applying a ground to our cathodes here we'll be able to switch on the relevant IGBT channels. Alright, so if I just go to DC volts now, relative to ground. Just go to one of my anodes here. Bingo! 5 volts on that one. 5 volts on there. So that means I should have gate drive power should pretty much be just flowing down through those anodes now. I'm probably going down to yeah, here we go. We got our LED voltage drops there on that, so we should be able to just ground those pins there and switch on some transistors. Now how I'm going to check if I'm switching them on, I've just got another benchtop multimeter here. It's just above the camera. What I'm going to do is just put some leads on it and set it on a diode test. What we're going to do is we're going to put our lead so that the positive lead from the meter is going to what will be the high voltage plus, which is this guy here, top one. I'm going to go to the L1 phase. So what we should have there then is you should pretty much have open circuit, which we do, because we're now looking for the high side on L1. And I'm going to get a bit of solid core wire here and just give myself a ground connection. Let me get a decent ground here so that I'm not making a complete fool of myself. Partial fool, yes, but not a complete one. So let me just put this on here. Just pick up a ground handy there. There we go. Alright, so a little bit of solid core wire. I'm just going to go around here and see what jumps out at me. I'm just grounding. Oh, there it is. We just found them. We just switched on our first IGBT, putting ground on this pin here. So what we'll be able to do then is pretty much just go from here to the pin header and work out what pin does what. So I'm going to go ahead and do that, and yeah, then we'll be able to turn on and off our IGBTs. Woohoo! Okay, so at this point we now have 8 gate drive signals, 8 fault signals, and our 4 5 volt power supply to the gate drive optos. So we're in very good shape here now. At the minute, this is really starting to take shape for us. So we have a couple of more things we need to work out. I'm going to leave probably the best for the last, which is going to be this weird gate power supply system. I'll kind of look at that lastly, but a couple more things here that we would like to get a look at. And probably the next target of opportunity is going to be the high voltage bus measurement system. So let's see if we can figure out how some of that works. Alrighty, so our high voltage bus is measured by this part of the circuit here. There's a transformer to provide isolated power, and we've a chip here. What could this be? Let's have a look at what it is. So it is the HCPL 786J, an optically isolated sigma delta modulator. Ooh, that sounds like so much fun. So sounds like we're going to have yet another filter that we're going to need to design, and I'm guessing that this is one of the tasks that Xilinx Spartan FPGA is performing. on the original board, which would be decoding the output of this guy to give the bus voltage. Alright, so let's have a look at our clock, if I can find my scope probe. 3, 4, 5. So this is our clock signal. Looks to be coming in at about 5 volts roughly, and 9.26 megahertz. So that's our clock. And our data, be just underneath that. Oh yeah, there's our data. So let's see what our data is looking like. It's pretty typical kind of 1-bit encoded data that'll be representing the bus voltage. Whoopee. Now, reading these sigma delta sensors is not exactly the nightmare that you might think it is. Because basically what the output is a PWM signal. And if you treat it as such, you can recover the analog data. Now this multimeter, as some of you may recall, fooled me back when I was reverse engineering the Tesla large drive unit into thinking that it had analog current sensors, because it was extremely good at filtering the sigma delta signal. Now I've just got the meter here on the MDAT signal, just on DC volts. It's giving me a very precise 2.400 volts. I'm going to flick a switch on a power supply here and put about 30 volts DC on the high voltage bus. It would be great if the multimeter wanted to stay on the pin for me. No, wrong pin, of course. I love live camera. So there we go, we're up to 2460. If I turn it off, see that'll dissipate down. If I go back on again, we go up to 2460. So we'll be able to recover that sigma delta signal just by use of a simple analog filter, probably an active filter, rather than all of this FPGA crap. Okay folks, I hope you've enjoyed this one. We've pretty much gotten everything that we need here. We've got IGBT drive, IGBT faults, DC bus voltage measurement, current measurement. I'm not going to go into too much with because it's very simple to get the pinouts. It's the LEM LAC 300S is the current sensor we're using here, or that Siemens are using. There's 4 of them. Heatsink temperature sensor, work that out, easy peasy. It's 16K at room temp here, but you know, we can replace that with any one we want. It's just on a little screw tab. So that's pretty much it for the reverse engineering stuff. There's a bit more I need to do around the IGBT drive, or sorry, not the IGBT drive, the IGBT power supply drive, but I'll probably come back to that in a later video when we have a circuit worked out. So, as I say, hope you've enjoyed. We will be making logic boards available for this inverter. I will even be making this inverter available as a complete package for people who want to just plug and play. And as usual, be 100% open source, so if you want to go off and do it yourself, and then don't give me any money and then I don't get paid. Oh well, who cares? you guys can go ahead and do it, and I will be putting up a GitHub repo for all of the info that we've gathered, and there'll be, as I say, the PCB designs will be on there as well. So don't forget to like, share and subscribe. Check the links in the description for Patreon and PayPal and anything else you can possibly find. And until next time, happy high voltage IGBT driving.